For our project, we modeled a car driving 50 meters to the end of a parking lot, turning around and driving back. We measured and marked different distances from the starting point and timed how long it took to drive to these distances to collect our data. This data was not consistent enough, however, to make a proper function, so we plotted our points and found a line of best fit to base our calculations off of.
Displacement is defined as the change in distance between the final and initial positions of an object. For the car started at 0 meters and ended at 0 meters, both measured from the front bumper of the car. So, over the interval of 0-30, the car's displacement was 0 meters because it both started and finished at the same position. Total distance is different from displacement. On the diagram, there are two red lines at 0 meters and 50 meters. The car started at 0 meters, it turned around at 50 meters, and then it came back to 0 meters. Therefore, the total distance traveled over the interval of 0-30 was 100 meters because it went one way and then came back, but both ways were 50 meters. The instantaneous rate of change at 1/3 t. Our t value was 30 seconds, so over the interval 0t when t equals 30 seconds, therefore 1/3 t equals 10 seconds. To find the instantaneous rate of change at 10 seconds, the derivative of the position function must be calculated, because the derivative of a position function is its velocity function. Our position function is boxed. F of t equals negative 0.25 t squared plus 7.5 t. By taking the derivative of this function, this gives the velocity function, which is negative 0.5 t plus 7.5. Now that we have the velocity function, 10 is plugged in for t in the derivative. After doing the math, the answer is 2.5 meters per second, the instantaneous rate of change at 1/3 t, or 10 seconds.
When we plug the slope into the point-slope formula, we can find the tangent line at 10 seconds. To do this, we first plug 10 into our position function to get a point. After finding the total displacement to be 50 meters, we use this point and our slope we found previously into the equation. With some simple expanding and addition to get y alone, we can see that the tangent line at 10 seconds is 2.5x plus 25. We can gain confirmation of this equation by seeing that our tangent line slope not only matches the curve at 10 seconds, but also goes through the point 1050.
To find the average rate of change between 0 and 1/3 t with our data, we had to find it between 0 and 10 seconds. We found the change in displacement, which was 50, then divided that by the change in time, which was 10 seconds, giving us an average velocity of 5 meters per second.
The change of the change is essentially the acceleration of our vehicle. It is found by taking the second derivative of the position function, or by taking the derivative of the velocity function. In this case, the velocity function, which is a linear relationship, has a derivative of negative 1/2, which makes the acceleration function a flat line and a constant. Although it may not make sense to have a negative acceleration since the vehicle returned to its starting destination, the negative 1/2 value for the acceleration represents the slope of the velocity line. From 0 to 15 seconds, the car is slowing down at a rate of negative 1/2 meters per second, and after 15 seconds, the car accelerates in the negative direction at 1/2 meter per second. Because the acceleration function is a flat line at negative 1/2, no matter the time, the acceleration is constant. So at 1/4 the time, or 7.5 seconds, the acceleration is negative 1/2. From this graph, the red line represents the position function, the green line is the velocity function, and the orange line is the acceleration function. It's interesting to see the regression in the functions, which in this case would be quadratic to linear to flatline, as the derivatives are taken. By just looking at the graph, it is evident where the change in direction occurs. This is found where the velocity function is at 0, which in this case looks to be just around 15. Additionally, at 15 seconds on the position function, we see a peak or vertex of the parabola, which also indicates a change in direction. To justify this, we use the velocity function negative 1/2 times the time, plus 7.5, and set it equal to 0. After some algebraic manipulation, we see that the change in direction is indeed at 15 seconds. From examination of each of the lines, we can draw conclusions about the nature of the particle's motion. In the 30-second interval, the car slows down on its approach to the maximum displacement of 50 meters. Then once it reaches 50 meters, it temporarily reaches a velocity of 0, where it then continues to accelerate in the negative direction. While a particle stopped at 30 seconds, if the car were to continue to travel, it would accelerate at 0.5 meter per second every second in the opposite direction.